All right. Some of this we saw a bit of a preview in Brian's talk, but I'm going to elaborate. I took a slightly different approach, so I will tell you that. We've been talking about this all day. We know there are a lot of threats that these corals face. Something in particular, some of these threats have a very explicit spatial attribute. Some have an explicit temporal attribute. Some are hard to track spatially, such as predation and things like that, because it's constantly changing, moving around. The data that I use and that I focused on is a data set from the Florida Reef Resilience Program. They've been collecting these data since 2005. This program was designed and supported by the Nature Conservancy. It's ongoing at the moment. It monitors coral condition throughout the Florida Red Tract, not just the southeast, but all the way into the Keys. And the data are available online at frp.org. They've also done a list of other things, including helping develop a climate change action plan for the region, understanding of how we actually use the reefs, and so on. So how do they collect the data? In a very brief description, they send divers down. They collect things like what actual species are down there, coral cover, how big the individuals are. They collect data on mortality, on bleaching, on disease. And this is the key to this data set that makes it different than a lot of these continuously monitored sites, is that they hit a new site every year. And so what you end up getting is a spatial spread throughout the region. In this case, in this four-county region, Miami-Dade, Broward, Palm Beach, and Martin, we have 675 sites that they sampled over the last 11 years, not including 2016's data. So to give you an idea of what that looks like, this is the sample point density. This is a kernel density map just showing you the hotter or the more red areas are where you have a higher concentration of sampling points. Of course, this is slightly artifact by where the reef actually is. But you can see some areas have more sampling than others. So, what do I want to do with this? Or what have I been doing with it? I wanted to ask if there are any explicit spatial trends in the data. So to do this, I want to actually model, sort of similar to the last map, but I want to model stress in the corals using GIS and model selection. So if I want to look at stress can be defined in different ways, but in this case, I wanted to combine these four metrics into one to define stress. They collected data on all of these, of course, percent paling, bleaching, disease, and mortality. Not only recent, but also old mortality. So to do this, I combine these four in this method. Essentially, it quantifies the percent of coral colonies that have either been recently affected by, or recently dead, recently diseased, or bleached, or paling. And this is basically just saying the probability of them being recently dead, or diseased, or bleached, or paling. You add it together. And what you get, final number, is a 0 to 1 score. 0 meaning there's no stress at that site, and 1 meaning it's 100% stress. The model selection process explains the aspatial variation in the data. So your final regression, whether you do model averaging or model selection using AIC or BIC, that explains relationships amongst variables, and in this case, stress. However, there's still a spatial extent. And you can model that completely separately using an interpolation technique like kriging, for instance. But regression kriging combines the two together. So what you have is your final model, and from that model, the residuals you can use to explain the spatial variation in the data. But then your final model will have important coefficients or parameters, and you can use those to generate a grid for each in GIS or in R, however you prefer. It's really simple, but you really add the layers together. Of course, they're multiplied by the coefficient from that regression. But what you get is a final model that's an interpolated model of the spatial data, but it also incorporates the aspatial variation from the regression model. which basically just means, so now not only do you have your real data points and values estimated in between them from the regression, or from the grading, but the regression model also informs that in-between zone, with the ultimate goal of making any predictions between known points better, refining those predictions.
Are you trying to make possible that after this long day it's out of batteries?
Hold on, sorry guys.
If it,
There, I turned it off and back on. Okay, so as I said, the spatial interpretation of this, or your final model is a heat map, essentially. So you can spatially interpret that heat map, but also we overlaid a hotspot analysis, which Brian mentioned earlier, which basically gives you this. The hotspot analysis is on the original data. It tells you when you have a statistically significant hotspot or cold spot. And then all of the white points means that they're not significant. So the difficult part is deciding what explanatory variables to include in your model to try to explain the variation in the data. You know, your question here is there something that's helping drive the stress of the coral, whether it's to be not stressed or to be stressed? And in this case, and again, they have to be spatially explicit. So these data were collected over 11 years, and I wanted things that were static, represented some sort of static aspect. So this is the list of variables. I'm not going to read them off to you. But the other key here, too, is, of course, every year there were new data points and new location samples. So there's going to be some variation explained by year, right? There's going to be some annual trends. Some years were hotter than others, so to speak. So to get rid of that up front, we did a regression with year on the data and took the residuals and moved forward through the model selection with the residuals from that. The idea being that we remove the temporal trend up front. And so now what we have left is we can ask spatial questions with the data because it doesn't matter necessarily what year they came from. When you run a full model in model selection, it runs every possible iteration of the model and it weights them based on MSCC. What this is showing you is a model average variable importance. So the way to interpret this, for instance, depth, this is saying that out of the top 100 models based on model selection, depth showed up in 100 out of 100 models as being important. And outfall distance showed up as being important in 97 of the 100 models. And so, of course, 80% is sort of an arbitrary cutoff, but what this is suggesting is that depth, outfall distance, distance to shore, and distance from an inlet are all important models in the top 100 models. For model selection, you choose the best model if you're not doing model averaging, and this is actually what the best model looks like. Unsurprisingly, it's the same 4 that we saw in model average. So you have an estimate for each, which tells you the relationship with your variable. So in this case, on the y-axis we have the lower it is low stress and high stress. Again, it's on with the residuals, so the scale looks kind of funny. So I put that. So this is saying right here, this is depth. I definitely can't read that down there, but this is the relationship with depth. So it's saying as the sites get deeper, the corals are less stressed. This is, again, throughout this entire region. This is saying the further they get away from outfalls, the less stressed they are. The further they get away from an inlet, the less stressed they are. And the further they are from shore, the more stressed they are. This one is kind of interesting to me, and I had that same at first too. I know you can't really see the point cloud very well. You can see a lot of them are sort of here in the middle, around 2 kilometers out. When you look at the final map of everything put together and overlaid, you can assess it in a few ways. You can assess the warm color areas, as well as the statistically significant hotspots. I don't know if you can see it too well, but for instance, there are those salmon-colored circles down there. So that's suggesting this little area is a hotspot down by this guy. There is another hotspot as you look right here. The nature center is like right here. So there's a hotspot by Dania Beach. There is another hotspot up by Hillsborough Inlet. And then as you continue up, there's a pretty nice cold spot up here by Palm Beach, actual Palm Beach proper. So again, there are a couple ways to interpret this. You can remember that what your top parameters were in your model. So again, inlet distance, outfall distance, shore distance, and depth. But you can also look at specific spatial relationships. So, you know, if you have a question of is one particular area worse off than another, you can use this map to ask those sort of questions. And remember, my goal was to look at just stress in general, but we also looked at each independent metric. So here's the map for bleaching. Remember, what this is basically saying is, for instance, let me pick a hotspot. Well, okay, so this is saying right here in this area, each one of these points experienced bleaching to some extent based on the data that we're collecting. Remember, we got rid of the temporal trend. So in bleaching, you see another hotspot, again, up by Hillsborough Inlet, and cold spots, again, by Palm Beach. And you can keep going through all of these. For instance, paling, same concept, another hotspot by Hillsborough, hotspot here by Dania Beach, cold spot by Palm Beach. Disease, we've been talking a lot about disease today. 2 hotspots nearby. One right here, just a little ways north of Biggers. And then again, Dania Beach is a hotspot for disease. One right here, and then we don't see that cold spot show up anymore, but it's also not a statistically significant hotspot by Palm Beach. And finally, mortality. You can see similar trends, but some areas, again, really stick out. Just north of Port Everglades sticks out. And again, here at Dania Beach really sticks out. And then another one up by Boynton. And you can, I didn't throw them up here because it would take a while to go through everything. But you can also look at the best model for each of these that further inform these regression models or these creeping models to try to explain the variation. So again, my goal was to try to understand factors that might be driving patterns of mortality, bleaching, or ultimately stress. I actually had thought I modified this to say that, oh, I put in the wrong spot. So I also create species richness and abundance to sort of give you an idea of what else is in this data set. So what this is suggesting, again, is a heat map. So the warmer areas here in the south implies higher species richness, and in the north, less species richness. But abundance is interesting. There's this pocket of really high abundance, and if you remember from a lot of the heat maps, that actually showed up as an area that, for instance, had high mortality, had high stress. So there's still plenty of other great questions to ask using this approach. So, as I mentioned, the FRP data set in its own right is sort of a gold mine with the sort of questions you can ask and address using the data. I wanted to clarify or reiterate some of the obvious problem areas when you look at this in a spatial context. Down by Biscayne National Park, near Government Cut, near Dania Beach, that one to me stuck out as the most prominent throughout. And out by Hillsborough Inlet. Cold spots, the 2 prominent ones were offshore from Hugh Taylor Birch State Park, right here, and up by Palm Beach. And now this is important to me because I feel like if you were going to prioritize an area where corals are either resistant or for some reason aren't experiencing stress like the other corals are, you might want to prioritize in an area like Palm Beach based on these data. Again, I wanted to also reiterate that regression kriging is a great tool because, again, it combines trying to describe the aspatial variation of the data with the spatial variation all in one model. And so I mentioned they haven't released last year's data yet. We've been talking a lot about 2016, a lot of these presentations today. So I'm excited to see, excited and a little nervous to see the 2016 data, but I intend to use this to actually test the predictions between already known points to see if this model holds up based on a new data set. With that, are there any questions?
So I thought it was a really interesting tool and obviously seems to be very useful for management. I just had a question about, I guess maybe I don't know the method you use very well, but R-squared you had was 0.05, which means that it only explains 5% of the variation, so that outlet distance and all that only together only explain 5% of the variation which you see. Is that because we're kind of putting too many species together? What do you think is causing that to be so low? Because
it's a good question, and there are a couple things that are potentially driving that, or to talk about. The first thing is that very initial regression with year to get rid of the temporal variation. That explained about 40%, so that R-squared was about 40%. And so not only did we want to get rid of the temporal trend, but what that also takes care of, again, are years where there was high heat or high heat stress. And with that, we don't necessarily have to use temperature as a variable. But what it also encompasses are stochastic events, like a dredging event or a storm that came through. So we already know these things affect corals, right? And they're, again, especially with like a dredging event, if it's a one-time event, it's hard to track that in an 11-year data set unless you're going by an annual basis, which you can do with this data. But again, the downside of doing that is now instead of having 650 some odd points, you reduce it down to the 100 or so for that year. So you lose the regression or the kriging prediction accuracy when you have so little points. The other possible explanation, or the other thing to address there too, is using a model selection approach. You're making two assumptions. Number one, that you've selected all of the most appropriate parameters to include, which is a big question, right? This is an extremely complex environment. Not only do you have things like straight line distance to shore or something like that, but you also have the three-dimensional aspect. We have, there's a south-to-north current, there's eddies that happen, and sometimes they happen periodically, sometimes it's consistent. Those things are very difficult to include in this sort of spatially explicit model. If there's a way, I am open to ideas. I would love to hear that. The other thing I was going to say there actually too is with multi-model selection, not that R-squared isn't as important. With the variable importance graph, that shows you again that out of the thousands and thousands of models it ran, the top 100, for instance, depth was important in 100 out of 100 models. While the R-squared was low, you still can't deny that depth is important, or it's an alias variable for something else that is important, but you're still getting close to an answer. If it's not the answer, but one of the answers. Long answer. Yeah.
I thought that was really interesting, Danny. Thanks for that. It looks like you're making good progress towards a PhD with John. I just have a comment that it's not stress, it's stress response. I mean, your aggregate is stress response. So the stress would be some aggregate of, for example, anomalously high temperature and cold temperature, duration of cyclone-generated wave, or water quality, tourism visitation, and maybe distance to shore as a proxy for sedimentation. Like that would be stress to me. So I only say that because I think it's interesting for you to maybe make that, even a rough version of it, and then map it to stress response that you already have, and then see how well it tracks. I know you say you might have some power issues because you can sample size, but even when you do that, I think you're going to see a strong trend. So what you're calling stress is stress response, and stress is going to be a good proxy or a good predictor of stress response. But what's interesting is when it doesn't predict it. So that's when you see that the stress was high, and you don't see as much impact as you expected. So you're in a sense, better set up than I've seen almost anybody to find relatively resilient or not so resilient reefs, just by changing the way you look at the analysis. I don't know if you had done already thought that, but it's something you could rough up in like a week, because we can produce the stress map pretty quickly, and then you can see if anything interesting plays out, where we find these bright spots or reefs imposed.
You're suggesting combining the actual stressors into a single unit, into a single metric?
I guess I'm suggesting, I thought that's what you've done by the name of the talk, but then I saw the stress response rather than stress. So if you made stress and then saw the extent to which you could predict stress response and worked out where it didn't predict it well, you might find evidence for relatively resilient or not so resilient reefs.
I guess the only possible hurdle there is defining stress in a spatially explicit way. Which is kind of what I was trying to get after by choosing things that don't move. You know, corals don't move, which is extremely convenient for this aspect. But outfalls also don't move. Well, not yet.
You have to scale up. For sure, you're going to end up at like 4 kilometers, but we can map stress in 4 kilometers for every one of the things that I mentioned. Okay, in a rough cut, you know, and then you have to aggregate some data within those 4 kilometer pixels that you can test it. I guess in thinking about doing a PhD, it's like, it's something you could explore, like how well does the stress predict the stress response? Especially if you're going to call it stress when like readers like me like, but it's stress response.
No, that's
like
a good
show that you explored that avenue of thinking.
Okay.
There could be an interesting result, actually really interesting results, potentially.
Maybe I'll talk to you. Yeah.
Good job, Danny. When I heard your talk today, it occurred to me that, I have a question for you. Are you able to normalize the data by the abundance or the richness?
Instead of using it as a possible explanatory?
Yeah, because you're going to have higher incidence of disease and bleaching in areas of higher density of corals. And so it might be something you'll want to consider to normalize your data, to take that variable out. Not richness so much, but certainly density some.
Well, I guess my thinking by including at least richness or abundance, and maybe there's a variable, like you said, that would be important to include, is that if it did explain some of the trend, that would show up in the model selection process up front. The thing I didn't include, like I said, the FRB did record was coral color and coral colony size. So maybe that could be a potential explanatory variable, maybe to incorporate to see if that is also possibly driving some of the patterns in the aspatial data.
And just looking at the distributions on this map and the richness map, if the high values match some of your consistent hotspot areas.
Right.
But go back to your diagram of the model selection. The threshold is 80%.
Oh,
threshold.
Carry more points.
That was
So richness, I don't know if you can read it from where you callers said, richness is right here. So that's suggesting it showed up as being important in about 22 of the top 100 models. So not that it's not important at all, it would be 0 on these lists. But it certainly isn't showing up in all of the top models. You can implement a model averaging process instead of selecting the top model, where you set a threshold of like 2 IC points, all models that are within 2 AIC points from each other. You model them together and you get an average unconditional estimate to use then in the regression group. That might be the way to go. That might account for some variables that might be in the third model that are not the top model. But in this instance, anyway, in the overall model, richness didn't seem to be that important. Yes.
I've got a question. If you go back to your abundance slide, so as Dr. Walker showed a little while earlier, down here, Key Biscayne in the national park, those are areas associated with very heavy seagrass cover. So I was kind of surprised that you're showing a moderate amount of abundance there. And then also I was really interested in if you are looking, especially for that one particular spot, it was defined out as a separation maybe potentially the stressors there is something that is related to the heavy seagrass cover, and the fact that that is kind of almost define a different type of ecosystem in that particular area.
So, I included bioregion. I don't know, I guess I glossed over that, or skipped rather. It was included in the full model. So, right here. So what that basically says in the model is, does being in one of those distinct defined bioregions affect whether they are more or less stressed or bleached or pale? And in this case, this is the overall stress response model. This suggested that it wasn't that important. I don't know if that answers your question.
I mean, just normally in very heavy seagrass bed areas, you're not going to see much coral cover.
And there weren't, if I can show you the point density, there actually was a bit of a spread there. I will tell you that I took out some points before doing these analyses. I also forgot to mention too, obviously Martin unfortunately was neglected here. There were some points up in Martin from the FRP, but they were extremely all close together, but isolated from everything else, and they were extremely variable within, which kind of implies we need some more data to be collected in the northern reach of our reefs. Obviously the reefs are narrower up there, there's less area of reef, but they're undersampled right now, at least in this data set. But I also weeded out some points that were not in appropriate reef habitat. So trying to restrict things to habitat. So if it were explicitly in a seagrass bed, that was not